Now, let's talk about antiderivatives of trigonometric functions. First, let's talk about the most basic rule, the standard rules. Derivative of sine is cosine, and derivative of cosine is negative sine. Consequently, the antiderivative of cosine is sine, and antiderivative of sine is negative cosine. We need 1 over a in order to undo the chain rule as before. Those are the first two rules. Rules 3 and 4 are related to tangent and cotangent. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. So we have antiderivative rules accordingly. Rules number 5 and 6 are relatively less important maybe, but still compared with others very, very important. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. Consequently, we have antiderivative rules accordingly. Please note that we have 1 over a because of the chain rule. Some additional trigonometric function rules. Okay, these are not as important, but here they are. Derivative of tangent, 1 over a log of secant. Derivative of cotangent, negative 1 over a log of cosecant. Derivation in forward direction is rather difficult, but if you start from the right hand side and then take the derivative, use some log rules and trigonometric function rules, then you can deduce these are antiderivatives. Alternative ways to write the same thing is to express log of secant into negative log of cosine, because secant is 1 over cosine and the log rule. And instead of negative log of cosecant, we can write log of sine. Again, cosecant is 1 over sine and log rule. Another couple of rules which are not really widely used are these: derivative of secant and cosecant respectively, and there they are. I've de-emphasized them in gray because they rarely appear. Here are some more rules. Antiderivatives of square trigonometric functions. These, if you want to memorize them, fine, but I think everybody should know the derivation as well. How do you calculate the derivative of sine squared? We use this half angle inequality or power reduction equality. Sine squared is 1 minus cosine of 2x over 2, which is equivalent to 1/2 minus 1/2 cosine of 2x, and then just apply antiderivative rule. 1/2 x, and then cosine becomes sine, and 2 has to be divided because that's my a value. So we have 1/4 sine of 2x. There goes the derivation. We can derive cosine squared in rather similar fashion. How about tangent function here? Well, tangent is secant squared minus 1, the Pythagorean identity, and antiderivative of secant squared is tangent. Antiderivative of 1 is x. That's how we get this identity. Rule for cotangent square can be derived rather similarly using Pythagorean identities. Well, here are some inverse trigonometric functions identities, and among these, arctangent sometimes appear either in this form or in that form. This one a little bit more often, but the others rarely appear. In any case, all the formulae are here. You know where to look up. Let's go over to some example problem. First, let's talk about something simple. How about problem A? This is really straightforward example. All I have to do is apply those extended version. A value is 3, so divide by 3. A value is 2, so divide by 2 and that's it. The other problems are not that simple. It is my intention that you review some trigonometric function rules, trig identities, while doing this. How do we handle this kind of problem? Secant times secant t, 2 tangent of t. How do we do that? Well, just like elementary function case, the very last thing you should do is to find out antiderivative separately and then trying to multiply. That's big no-no. What you need to do is break up the parentheses and then apply appropriate rules one at a time. So let's go ahead and do that. Break up, and we have secant squared minus 2 sec t tangent t. Don't they look familiar? Antiderivative of secant squared is tangent. Antiderivative of secant t tangent t is secant. Consequently, we have this function. Okay, how about some other problems here? How about problem C? Again, it is going to be a bad idea trying to find out antiderivative of numerator and antiderivative of denominator separately. The standard technique applies. Separate the numerator, and let's see what happens if we do that. 3 over sine squared, 4 sine squared over sine squared. Looks like we're going to have cancellation in my second term. How about the first one? Turns out that 1 over sine squared is 1 over sine squared is actually cosecant squared. So this part can be rewritten as 3 times cosecant squared v, and then this part will become just 4 after simplification. Antiderivative of cosecant squared is negative cotangent, so we have the antiderivative completed here. The very first step wasn't that bad because it fit into standard technique, separating the numerator. And then the second term was simple, but the first term you had to use some trig identity, which shows up all those places out of nowhere. Sine squared and tangent squared. By the way, we talked about these problems already. Sine squared, we use power reduction formula, and then applying antiderivative rule for cosine, we have sine. Just for exercise, let's do the problem for cosine squared. What is antiderivative of cosine squared? The power reduction formula works like this: 1 plus cosine of 2x over 2. Consequently, the only change is this plus, and applying those antiderivative rule, cosine becomes sine, and 2 is divided extra, so we have 1/4. The only change is negative to positive compared with sine squared case. Likewise, you'll have to prepare to use some trig identities in all these problems. Last problem is somewhat of a challenge. It does not really look like this one belongs to trigonometric functions and inverse trig functions. Amazingly, it does. As a matter of fact, you will see that this is not out of ordinary in Calculus 2. rational functions very frequently generate inverse trig function, particularly arctangent function. What am I talking about? Let's see. Decompose denominator into complete square plus 1. We have complete square plus 1, yes. And this complete square is x plus 1 squared plus 1. So we are in arctangent functions form. Derivative of arctangent is 1 over x squared plus 1. So this is arctangent of x plus 1. And there are a lot more problems about trig functions, so I'd rather refer to homework problems and WebAssign. Let's go over to some initial value problems this time. First problem, actually both of these problems are related to some physics and electric engineering in particular, because sines and cosines can be used to model alternating currents or light rays and sound waves and so on. The derivative is given, so finding out the original function will be done by antiderivative computation. That's not too difficult. Cosine becomes sine, and then we multiply the reciprocal, 2/3, 3/2, excuse me, times 2, generating this. Now, how do we identify this arbitrary constant c? By the initial condition. Plug in t equal to 0. We have 3 sine of 0 minus pi over 6 plus c. And what is sine of negative pi over 6? It's negative 1/2. So what we end up with is this is negative 3/2. So flip it over to the other side, then plus 3/2. So we end up with c equals to negative 1/2. Now that we identified c, we can plug it back to this x of t and then determine x of t. 3 sine of 2/3 t minus pi over 6 minus 1/2. Okay. The next problem is a little bit harder, but this one is also really important outside mathematics, especially in physics and engineering. Now we have second derivative. In order to find out x of t, we have to find out x prime of t, and then take antiderivative again to find out x of t. So let's start from taking antiderivative. Calculate the antiderivative. Then we have, well, this function, sines and cosines, simply enough. We have plus c. And then calculate the antiderivative again. We have this function and ct plus d. We have two constants, c and d. Therefore, we need two conditions to generate two equations. Let's plug in, let's use the first condition. X of 0 is negative 3. So plug in t equal to 0 to the second, and then plug in t equal to 0. Sine of 0 becomes 0, cosine of 0 becomes 1. So we have negative 2 plus d is negative 3. From that we can calculate the d value. It is negative 1. Let's use the other condition, x prime of 0, plug it in, and then sine of 0 is 0, cosine of 0 is 1, so we end up with negative 3 plus c equals to 1. Consequently, we got c value. Putting all those together, then we're going to get the final solution. Here we go.